Okay, today we're going to be looking at correlation. It's the first statistical analysis where we're going to be looking at two variables, two numeric continuous variables. So previously we've seen one numeric variable broken down into groups that we measured, but now we have two measured numeric continuous variables, and we want to see if they have an association. Okay, correlation does mean association in everyday use, and that's really the same thing in statistics. Okay, so, but instead of when one thing happens, another happens for a positive correlation, what we're going to see is that means as one variable goes up, the other variable goes up, or they both go down together. On the other hand, we'll see negative correlations, and that's not going to be when one thing happens, another doesn't. We're going to see that is one variable going up while the other one goes down. So the most popular measure of correlation is the Pearson correlation coefficient. It falls between -1 and 1, and it does cross 0. -1 and +1 would be perfect correlations, and 0 would be no correlation. And one thing we should be aware of is that when we're measuring correlations between two numeric continuous variables, there are certain types of biological variables that have low repeatability. And at the back of your chapter, there's a nice correction for this correlation coefficient when you are measuring biological variables that are very difficult to get the same measurement over and over again, low repeatability. But we're really not going to worry about that here. You should just know that's out there. So as I said, R is a linear correlation coefficient, or if I didn't, I'm saying it now. So it's measuring the relationship, the association between two numeric continuous variables, but it has to be in a linear pattern, in a line pattern. We don't actually draw lines on our scatter plots that we make for linear correlation coefficients, but we can imagine a line going through there. So in this first graph, you can see perfect positive correlation. X goes up, Y goes up. All those dots would fall on our imaginary line. In the second one, there may be a mathematical association there, but it's not linear, so R is going to be 0. And like all the sample estimates we have been measuring, this R is a sample estimate for the truth, which is called rho. So let's look at some scatter plots of two variables and their correlation coefficients. Scatter plots are very important for us and is the first type of graph that we're going to make when we want to even examine whether two numeric continuous variables are associated in a linear pattern. So in the first graph, R equals 0, we can see just this scatter of plots in no particular pattern, and so it does not appear that there is any linearity between X and Y as a relationship. In the second one, we can see that these dots are kind of pulling together, still kind of spread apart a bit, but pulling together where we can clearly see that as X goes up, Y appears to go up. And so we have a positive correlation coefficient of 0.5. Third graph, negative, because in this case we can see as X goes up, Y goes down. So we get a negative correlation. And those dots are pulling together even closer along what we could imagine a line going through all those. And in the last one, those dots are even pulling even closer together along that linear pattern. In a positive correlation, X goes up, Y goes up, so our correlation coefficient is 0.9. So the correlation coefficient R, and let's see how we calculate it and what we're really looking at. We're measuring the tendency for each value in the variable and how it deviates from its own mean, and how that's accompanied by the deviation from one mean to another. So in ANOVA, we saw this idea of residual. Well, that's deviation, so distance from any point from its own mean. And so that's what we're going to be measuring in our R calculation. It's standardized. It does not matter how X and Y were measured. If you had, height and weight, centimeters and kilograms, it does not matter because it's standardized. But as we already saw, it's signed. It tells us the direction of the association, and that's important. So the magnitude of R tells us the strength of the linear correlation, and the sign tells us how those two covary together. So you can see that general R calculation below. It's covariance of X and Y over the standard deviation of X and Y. How do we calculate that? Let's break it down some more. So covariance of X and Y, as you can see, is the sum of every X value minus its mean. See, there's a residual or deviate. You can call it either one, times every Y point in its distance from its mean. And the timesing of those two is called the sum of cross products, and it is divided by degrees of freedom. This should look a little similar because it looks like the variance calculation we've done before a long time ago, and now we really saw it again in the ANOVA. So very similar to a variance, but now you can see two variables covariance, how each one is changing, how it's deviating from its mean together. Okay, we can now plug that covariance calculation into our R calculation we saw previously, and with some rearrangement, we can see how we have 1 over the standard of X, standard deviation of X times standard deviation of Y equals the sum of those deviates, cross products, over degrees of freedom. Algebraically moving things around, we come to our third line, especially in the middle there. Now, this should look a little familiar as well. Like a z-score, remember this? Distance of the value from its mean over the standard deviation. So now we can see that what we're really talking about to get an R is if we sum up the z values for every x and y value and divide by the degrees of freedom, we're going to get our R calculation. And because it's a z, that's the standardization of those scores, so that's why units don't matter here. Sidebar, lots of R calculations. They're equivalent algebraic expressions. Don't worry about it too much. Mostly we're going to be getting R's automatically from Minitab and or Excel. So once we get an R, as I said, it tells us about the strength of a linear correlation between two numeric continuous variables. So an association between them. And then the sign matters for the direction of how those two variables change in regards to each other. If there is no correlation, that would be known association between the variables, and that they're independent. So what we want is, not only do we want to get that R calculation, but we want to have a hypothesis test to tell us if this R we got is statistically significant. Okay, and we are going to use a t-test. Yay, we know all about t-tests, so that's easy. So we have a null and alternative hypothesis. The null is the R is 0. That would mean no association, no linear correlation coefficient, no linear association between variable 1 and variable 2. They're independent of each other. The alternative is that R, and look, it's the absolute value because it's still about the magnitude away from 0, is not 0, and that these aren't independent of each other. So we're going to pick a t-test of the correlation coefficient to calculate to then tell us if we're going to reject or retain our null that R equals 0. Alright, so we're going to calculate our observed R, okay, used a slightly different R calculation, doesn't really matter because again we're going to get it from Minitab or we can get it in Excel. There we go. Calculate our test statistic. Hey, this should look a little similar, but this time we have R over the standard error of R. And the calculation for standard error of R is below. And then we're going to do just like we've done, right? We're going to get our test statistic, our t-stat. We're going to compare it to t-critical and our p to alpha. The only thing we need to understand here is that the degrees of freedom for this is n minus 2. And that's basically because we had to calculate R before we could calculate T. So we lost another degree of freedom. Okay, and this is just the decision to reject the null. It's the opposite to retain it. This should sound very similar. If p is less than our alpha set at 0.05, we reject. If our t statistic is greater than our t critical, we're in rejection. Okay, and of course, if we reject, we conclude that there's a significant linear association between these two variables. Of course, there's assumptions. Okay, random sample of the population, yes. X and Y are bivariate normal. Now that's hard to see. The first graph there, the 3D sort of graph, is a graph that you might be able to create to see bivariate normal. We're not going to be able to do that. Here's what you're going to look for. You're going to do the scatter plot. You should see a linear pattern between these data points. That linear pattern should look like that second graph, sort of a cloud of points, circular, not super circular, more elliptical, elongated circular elliptical shape. If it's too circular or some other weird pattern, that another mathematical formula might be appropriate, not linear, then we don't want to use R. And X and Y are each normally distributed. We can do that with our AD and P values, so we're still going to check that assumption. And if those are normally distributed and you see the linear relationship on the scatter plot, you should be fine for the assumption. Here's some ideas of what you might see on a scatter plot when you are violating the bivariate normality. So in the first one, there's a funnel shape. And in the third one, there's a clearly non-linear pattern. The second one I want to talk about last because outliers are something we really need to be cognizant of when we're looking at our scatter plots. Outliers can really change our measurement of R in terms of the strength or the magnitude of that. So you can see in this middle one, that outlier over there is probably going to try and create a positive correlation because that outlier is up in the upper right corner. If we move that outlier to the upper left corner, that would totally change the R calculation we get. And so we really need to understand if an outlier is there, why, if it's real, and whether it's going to preclude us from doing a correlation analysis. The size of R depends upon the range, right? So a larger range might denote a stronger magnitude in our linear correlation, where if we select a subset, it could weaken it. And finally, correlation is not causation. We cannot say because there's a correlation between two variables, an association, that one causes the other. Okay, and there's no predictor, no response. In correlation, we're going to get the same answer whether we interchange X and Y variables on our graph. There's some famous, good examples of correlations that are significant. Spring arrival of migratory birds and onset of the growing season, the lengths of our arms, the lengths of our legs. Okay, they occur together or may have a very strong correlation coefficient, high R, either in the negative or positive, but that doesn't mean one causes the other one. So you might ask, why do we look at them? Well, we want to see if there is that interesting pattern that bears additional studies. And in some cases, what we're going to really wonder is, would modeling under a linear regression then be appropriate for two variables?